2009, paleoanthropologists working in the Afar region of Ethiopia discovered a new fossil, and it didn't make a lot of sense. The fossil was named the Burtele Foot, and it was dated to around 3.4 million years ago, found at the Voronzo Mile site, specifically in the Afar region in Ethiopia. This is significant because this is around the same time and place as Lucy's species, Australopithecus afarensis, was walking around the African landscape. Cool, you might be thinking. So the Burtele foot must belong to Australopithecus afarensis, Lucy's species, right? Nope, because the Burtele foot looks like this. My keener-eyed viewers may notice looking at this fossil that it kind of looks like a chimp or gorilla foot. It has a big abducted or opposable toe. That foot can't belong to Australopithecus afarensis because we have Australopithecus afarensis foot bones and footprints, and they don't look like that. In the overwhelming majority of ways, Lucy's species' feet looked like our feet. They have an inline big toe, or hallux. They have 3 arches in the foot, and the toe bones themselves aren't as curved as what we would see in fully committed arboreal apes. And those observations extend to other species of Australopithecus for which we have foot bones. Fossils attributed to Australopithecus africanus and Australopithecus prometheus, if you split those guys out, show the same inline hallux that is non-opposable and very human-like that we see in Australopithecus afarensis. Australopithecus as a genus first emerges in the form of Australopithecus anamensis roughly 4.3 million years ago, and virtually every Australopith big toe or hallux that we have seems to be oriented in line with the rest of the toes. One reasonable inference then is that by the origin of Australopithecus, that big toe was already in line with the rest of the toes. It was no longer opposable by the start of that genus, and thus everyone in that genus, all Australopiths, have inline halluces, or big toes. That's reasonable, I think. But if that change was cemented in genus Australopithecus by 4.3 million years ago, what's this guy doing with an opposable big toe almost a million years after that? Who is this? Well, 15 years later, the original discoverers of the Burtele foot are back with an answer to that question. Let's talk about how we solved the mystery of the Burtele foot and what implications this new identity has for our understanding of human evolution. Now, one idea you might have had is, why are we saying this is a human relative at all? Maybe this is an ancestral chimpanzee or a gorilla. After all, it does have that big opposable toe. That's a really good question. Let me walk you through it. Humans and our closest living relatives, the panins or the chimpanzees and bonobos, split from one another approximately 7 million years ago. And any ape that is more closely related to us than it is to chimpanzees or bonobos, that is to say, on the human side of that split, is called a hominin. The first species generally accepted to be hominins are Sahelanthropus chidensis at about 7 million years ago and Aurorantuganensis at about 6 million years ago. Humans differ from other living great apes or hominids in 5 major ways. 1, we have really big brains for our body size. 2, we walk upright or bipedally, and that includes a lot of skeletal and muscular differences. 3, we have small canine teeth that don't keep themselves sharp and are the same size between the sexes. 4, we take a really long time to grow up. And 5, we have an extremely broad diet and tool culture. Human evolution then predicts that we should see those 5 characteristics emerge slowly through geologic time from 7 million years ago to present day. We should see the acquisition of the traits that make a human in the fossil record, in these fossil hominins. So the first hominins then should have mostly generic Miocene ape characteristics, but just a handful, just a smattering of human-like characteristics. Sahelanthropus chidensis and Aurorantuganensis each have some kind of controversial bipedal signals in addition to an overall upright or orthograde posture, which, as you can imagine, necessarily precedes those bipedal characteristics, but both of them also have reduced canine teeth that appear to be sexually monomorphic that can't keep themselves sharp, and that is generally accepted as the first hominin characteristic to evolve. Put simply, our first relatives after the split with chimps and bonobos were upright in posture, but probably not committed bipeds, with small, dull canine teeth that were the same size between the sexes. Okay, I say small and dull. They're small and dull compared to something like a chimp or a gorilla. They're actually still pretty impressive overall. And that makes sense because they're going to further reduce and further lose that canine P3 honin complex as we move along through hominin evolution. The Sahelanthropus chidensis remains and Aurorantuganensis remains are both pretty scrappy. Most of the skeleton for these hominins is unknown, but luckily that is not the case for the next hominin genus, which is Ardipithecus. Ardipithecus cadaba, the older of the two species within this genus, isn't very well known either, but Ardipithecus ramidus, the younger of these two species, dated to approximately 4.4 million years ago, is represented by a wonderful collection of fossils, including a partial skeleton. This partial skeleton of Ardipithecus ramidus is dated to 4.4 million years ago, approximately, and it preserves an incredible amount of detail with regard to the anatomy of this species. Many of the trends that are seen and generally accepted in Sahelanthropus and Auroran are continued in Ardipithecus ramidus, specifically that orthograde or upright posture, which is indicated by the position and angle of the foramen magnum, or hole at the base of the skull. We know that this thing's skull sat directly on top of its vertebral column and that it held its body upright. The canines are further reduced and that canine P3 honin complex is all but gone. Artie's torso, arms, and hands are all very apish and primitive. This thing definitely was at home in the trees, but when you reach its pelvis, we start to see yet more hominin characteristics. Of the three bones that make up each side of your pelvis, the ilium, ischium, and pubis, Ardipithecus ramidus has a human-like ilium, but a primitive ape-like ischium and pubis. But the minutiae of the anatomy of the ankle and foot reveal a much more complicated picture. Some aspects of this ankle and foot for Ardipithecus ramidus are more like later hominins. This, in combination with all of the other hominin characteristics for the Ardipithecus ramidus skeleton, let us know that this thing is on the human side of the chimpanzee hominin split. The foot is where things get really interesting. That's not the Burtele foot you're seeing, that's the Ardipithecus ramidus foot that you're looking at there. It looks really similar though, doesn't it? It was found first in 2009, or rather decades before, but published on in 2009. And it has that same divergent opposable big toe that we'll see in the Burtele foot 3 years later. And like the Burtele foot, at first glance, you would be forgiven for looking at the Ardipithecus ramidus foot and saying, why aren't we proposing that that belongs to a chimp or a gorilla relative? Now, the main reason is because those feet are attached to a decidedly hominin body. Remember, there's hominin marks all across the Ardipithecus ramidus skeleton. That thing is clearly not a panin. But believe it or not, there are actually parts of the feet themselves that tell us that this foot belongs to a hominin and not a panin relative. Let me make a comparison with modern non-human African apes versus modern humans first. In non-human African apes like chimpanzees and gorillas, we see a really flexible ankle, a really flexible midfoot, an opposable big toe, obviously, to allow them to grip, and flat feet with no arches. In comparison, humans have a much more stable ankle, a much more rigid foot with 3 arches for shock absorption and sort of rolling our weight through, and an inline big toe that can't grasp. Ardipithecus ramidus has the African ape-like condition for its first 2 toes in order to allow them to oppose, but it has the human condition for the last 3 toes. It has a rigid midfoot, but a flexible ankle. It's mostly like African great apes in that it could use its feet to grip the branches, but when this thing came to the ground, it had a stable, rigid enough lateral foot to sort of roll its weight through as it walked. And we know from its posture that when it walked, it would have done so bipedally, upright. It's worth noting, too, that it would have had to come to the ground where it would have walked upright quite a bit, because the reconstructed environment for this hominin on the base of isotopes and faunal assemblage seems to reflect a patchy woodland broken up by grassland. It couldn't have stayed in one forest for its entire life. It had to come to the ground to move to other trees. So, okay, you're thinking, the Burtele foot isn't a foot that belongs to a chimpanzee or gorilla relative. It does belong to a hominin, and that hominin is a member of Ardipithecus, right? That's what you're thinking. Except the genus Ardipithecus emerges 5.7 million years ago and doesn't seem to persist past about 4.4 million years ago. And that Burtele foot is, again, almost a million years younger than that. So are we to suppose that Ardipithecus, the genus, did persist for an additional almost million years, but left no trace of itself during that entire time period, except for that one foot? And then there's the other elephant in the room, which is that the Burtele foot doesn't look like the Ardipithecus ramidus foot once you get down into the details. Most obviously, that big toe is less divergent in the Burtele foot as compared to Ardipithecus ramidus, but the Burtele foot also doesn't have Ardipithecus ramidus's curved toes, and the Burtele foot, unlike Ardipithecus ramidus, has one foot arch, the transverse arch. The original publication is just loaded with cool minutiae about where the Burtele foot differs from Australopithecus, or from Ardipithecus, or from modern humans, or from other non-human African apes. My favorite of which is that the Burtele foot's fourth metatarsal is longer than the second metatarsal, which is evidently something that we don't see in anything else ape-wise. So the authors in the original publication were essentially like, we can't place this thing reliably, especially because there's no craniodental remains along with it, which tends to be super diagnostic for hominins. Who did the Burtele foot belong to? Maybe it was a late surviving member of genus Ardipithecus that we just haven't discovered yet, and this foot is all we have of it. Maybe it was from Kenyanthropus platyops, who was lurking around on the landscape around this time and for who we have basically nothing except for craniodental remains. Or maybe it belonged to a species of Australopithecus with a very different foot than the foot that we're used to. The title of the article, New Finds Shed Light on Diet and Locomotion in Australopithecus Diorama, probably gives away the punchline as to the identity of the Burtele foot. Now, upon hearing that, you might be thinking, what? What is Australopithecus Diorama? Depending on who you talk to, during this time period of roughly 3 to 4 million years ago, in Central and Eastern Africa, there is either one hominin species called Australopithecus afarensis, or substantially more than that. In paleontology generally, you will run into lumpers versus splitters. Lumpers typically propose that there are species which span long periods of time and contain a lot of variation within them. Australopithecus afarensis is one example, but another one you've probably heard of is Homo erectus. Some people think that Homo erectus is a single species that lived for 2 million years and is very diverse. Others would say that what we think of as Homo erectus is actually Homo georgicus and Homo ergaster and Homo erectus, and that each of those species contains less variation than lumping them all together in one very diverse group called Homo erectus. The same is true for Australopithecus afarensis between 3 and 4 million years ago in Central and Eastern Africa. A splitter would say that what we considered to be Australopithecus afarensis from a lumping perspective is better understood as a Central African species called Australopithecus barrel-ghazali, a dentally unique but contemporaneous hominin called Australopithecus diorama, which lived alongside Australopithecus afarensis there in Eastern Africa, but specifically Ethiopia, and a slightly more southerly hominin, a Kenyan native from the side of Lamekwi called Kenyanthropus platyops. That's right, this hominin would belong to a completely different genus and species as compared to Australopithecus afarensis. Of these species, Australopithecus diorama was one of the more controversial ones, whereas most people accept Kenyanthropus platyops and some people accept Australopithecus barrel-ghazali. Australopithecus diorama had the added sort of problem of being in the same place as well as at the same time as Australopithecus afarensis. The species was named on mandibular and maxillary remains, as well as the teeth found within those mandibles and maxilla, which are very diagnostic, but some people didn't think that they were diagnostic enough. Remember the concept of competitive exclusion from ecology, where two species cannot try to fill the exact same niche, or one is going to go extinct due to the competition between them. If two species are vying for the same niche, one has to specialize out of it. And in the case of Australopithecus diorama, the teeth weren't necessarily hitting everybody as so distinct from what we were seeing with Australopithecus afarensis, so as to be safe from direct competition with it. So instead, maybe they just were a part of the same species, and then there's not really a problem with competing with one another. This paper is going to reveal that Australopithecus diorama is not just distinct from Australopithecus afarensis, but it is very distinct. So let's start, as we always do, with the abstract here. The naming of Australopithecus diorama from Voronzo Mille, less than 3.59 to more than 3.33 million years ago, indicated the presence of a species contemporaneous with Australopithecus afarensis in the Ethiopian Afar Rift. A partial foot, the Burtele foot, and several isolated teeth from two Burtele localities, however, were not identified to the species level. And keep in mind that Australopithecus diorama was named after the Burtele foot was found. So there was an opportunity when naming Australopithecus diorama to say, and also that foot belongs to this species, since they were found so close together. Recently recovered dentognathic specimens clarify not only the taxonomic affinity of the Burtele hominin specimens, but also shed light on the diet and locomotion of Australopithecus diorama. Here we present a comparative description of these specimens and show they are attributable to Australopithecus diorama. We also find it parsimonious to attribute the Burtele foot to this species based on the absence of other hominin species at Burtele. The new material demonstrates that overall Australopithecus diorama was dentally and postcranially more primitive than Australopithecus afarensis, particularly in aspects of its canine and premolar morphology and in its retention of pedal grasping traits. That's that Burtele big toe. Furthermore, the low and less variable distributions of its dental enamel C13 values are similar to those from Ardipithecus ramidus and Australopithecus anamensis, indicating a reliance on C3 foods. This suggests that Australopithecus diorama had a dietary strategy similar to the earlier Ardipithecus ramidus and Australopithecus anamensis. The Burtele foot and its assignment to Australopithecus diorama provides conclusive evidence that arboreality was a significant component of the positional behaviors of this Australopith, further corroborating that some degree of arboreality persisted among Pliocene hominins. So, to summarize so far, the authors are proposing that the Burtele foot belongs to Australopithecus diorama, and that in addition to the Burtele foot, several other fossils can be attributed to this species, broadening the diagnostic characteristics of Australopithecus diorama. So if you accept these results, there are now way more characteristics that can sort of clock this species and that separate it from Australopithecus afarensis. In addition to this, an enamel analysis revealed that Australopithecus diorama is primarily feeding on C3 plants as compared to the much broader diet that we see in Australopithecus afarensis, allowing these two species to live in the same place without having to directly compete with one another. And presumably, Australopithecus diorama is able to exploit those C3 resources using, in addition to other characteristics, that big grasping toe, because a lot of C3 resources are located in the trees. That is fascinating and kind of wild, but not really that surprising when taking into account what we've been continuing to discover about hominin contemporaneity at virtually every site and virtually every time. Contemporaneity just means that there's more than one species living on and exploiting the landscape without having to come into direct competition with one another. Humans and Neanderthals, humans and Denisovans, Denisovans and Neanderthals, Homo erectus sensulato, and anything and everything across its 2 million year tenure. Just the entire muddle in the middle. Early genus Homo and Paranthropus, early genus Homo, Paranthropus, and Australopithecus sediba or Australopithecus garhi. There are countless examples at this point, and I think it's almost fair to say that contemporaneity might just be the rule rather than the exception when it comes to hominin diversity. Now, I'm not positive on this, but I'm pretty sure this is like the oldest example of hominin contemporaneity in the fossil record, right? Like we have Sahelanthropus and it's kind of by itself, and then we have Auroran and it's kind of by itself, and then we have Ardipithecus cadaba and Ardipithecus ramidus, but that's kind of an anagenetic lineage, or at least it's thought to be. Then you have Australopithecus anamensis, which maybe was overlapping with Ardipithecus ramidus or Australopithecus afarensis after it, but it's not as solid as this, where we just very clearly have Australopithecus afarensis and Australopithecus diaramida, and they're living on the same landscape and exploiting different things. That's really cool. The first little bit of the main text summarizes what we've talked about so far. They talk about the Burtele foot potentially being related to Ardipithecus. They say some researchers have argued that the presence of human-like feet in some members of early Homo, variability in the foot morphology of Australopiths, and a foot with opposable hallux in some of the earliest hominids such as Ardipithecus ramidus all suggest diversity in pedal adaptations for bipedal locomotion. That's true. I don't think that's controversial. Most people at this point, especially with the Laetoli trackways and what we've seen from some of our Australopiths and Paranthropus, accept that hominins were moving in similarly bipedal ways, but not necessarily identical bipedal ways. More recent studies have further suggested that the Burtele foot demonstrates the presence of variability in foot morphology and bipedal locomotor adaptation among species of Australopithecus, whereas others have hinted that the Burtele foot belonged to a late surviving species of Ardipithecus, despite there being differences in the morphology of the first metatarsal and the metatarsophalangeal joints. So the question, right, is the Burtele foot an Australopith, or does it belong to Ardipithecus? Because if the Burtele foot belongs to Ardipithecus, that's just a continuation of that big divergent toe, and that kind of leaves the foot morphology of Australopithecus as we understand it untouched. But if the Burtele foot belongs to Australopithecus, then that means that there's a lot more foot morphology diversity within this genus than we've previously appreciated, and that seems to be the case. Some people might say, well, why did we assume that for Australopithecus until now? And the answer is really simple, because until now, there wasn't an exception to the trend that Australopithecus foot remains indicated in inline big toe, the full 3 arches, and so on and so forth. That's the wonderful part about science, is we can revise our perspectives when new data come to light. Now, to be clear, this doesn't change the fact that for most Australopiths, at least in the case of Australopithecus afarensis, Australopithecus africanus, and Australopithecus prometheus, as well as inferences on other closely related taxa like Australopithecus sediba, those guys are still like well characterized as having that inline big toe, those 3 arches in the foot, when we have the fossils, and so on and so forth. What this does for us, what Australopithecus diaramida and the Burtele foot does, is it tells us that we didn't see the sort of extinction of that divergent big toe with the transition of Ardipithecus to Australopithecus, if that indeed is a transition that occurred, as opposed to Australopithecus having a different sort of progenitor genus. Instead, it seems that early Australopithecus, and we're going to get to this in a second, may have been more generally characterized by this divergent, less so than Ardipithecus, but still divergent hallux or big toe, in addition to that single arch in the foot. It's almost like every species is transitional. Cool. So they continue to talk about why the Burtele foot wasn't initially ascribed to Australopithecus diaramida after it was named, and they go on to say the Burtele hominins retain a more primitive Australopithecus anamensis-like dental features than Australopithecus afarensis, and there's now evidence that, like anamensis, they had a C3-dominated dietary adaptation. So what they're saying here is that you have the very first member of Australopithecus, that's anamensis, and then you have Australopithecus afarensis after that. Diaramida kind of fits in that slot between, where it has more features like Australopithecus anamensis than it does Australopithecus afarensis. Of course, a species doesn't have to go extinct just because it yields a new descendant species. We have dogs and wolves today, even though dogs descend from wolves. It may be that Australopithecus afarensis descends from Australopithecus anamensis, and Australopithecus diaramida is just sort of a continuation of whatever Australopithecus anamensis was doing. And I know you're probably already thinking it. What does that mean for the morphology, including the foot morphology? of Australopithecus anamensis. We'll get there in a second. So they continue down talking a little bit about the stratigraphy and provenience of these new fossils. The geological age is a big one that has to be sort of cemented, especially to like contextualize Diorama within the sort of Australopithecus genus as a whole. They talk a lot about the new dentition and the comparative analysis of the teeth here, talking specifically about the incisors and the canines and the premolars and the molars, but those canines and premolars being the most sort of characteristic for Australopithecus diorama as compared to afarensis. They talk about the deciduous teeth because they've got some like kids in this fossil assemblage, which is a little bit morbid, but also pretty interesting. Figure 3 has a nice sort of comparative analysis of like where these things fall with relation to one another. I like the teeth stuff, but I'm not like a teeth person outside of just the canines, so we're just going to continue to the postcranial evidence since we are talking about this entire discovery with relation to the Burtele foot, right? The postcranial evidence includes the Burtele foot as well as a new juvenile ischium, so that's a part of either side of your pelvis. If you'll remember earlier, I said both sides of your pelvis have 3 bones that are fused together. You have your ilium, you have your ischium, and you have your pubis. They have a kid ischium here, which is pretty cool, and we'll talk about it in a second. The spoiler is that it's not like substantially different from other Australopith ischia, but we'll talk about that in a sec. First, the foot. They say the partial foot displays morphologic features that suggest a greater ability for grasping than in modern humans and most fossil hominins. Okay, we know, right? We talked about that already. Here they summarize it, and then they say this is in stark contrast to the foot morphology of Australopithecus afarensis and provides further evidence for Pliocene hominin locomotor diversity. The divergent hallux of Ardipithecus ramidus clearly differs from the comparatively more adducted, less mobile hallux of Australopithecus afarensis, principally based on the morphology of the medial cuneiform and its articular relationship with the first metatarsal. All they're saying here is that the big toe of Ardipithecus is more divergent for the opposability, and the big toe of Australopithecus afarensis, Lucy species, is more in line and actually can't oppose, and that's due to not just the toe itself, but the tarsals that articulate with those toes. Figure 5 shows the breakdown of the foot morphology. I'm going to focus on B, C, D, and E here. So you can see Pongo, that's orangutans, in yellow, and then 2 gorillas in blue. Pantroglodytes and Panpaniscus, so our bonobos and chimps, they're in purple, and then humans are in red. And our 3 little black sort of symbols here. The dot on top is Ardipithecus ramidus, this dot below is Lucy's species, Australopithecus afarensis, and the star is the Burtele foot. So it's basically telling you where the Burtele foot maps across these 4 different characteristics. The relative depth of the first metatarsal head, or the head of the big toe, it's mapping pretty strongly with Ardipithecus and the African great apes. With regard to the relative width of the dorsal, so the top portion of the first metatarsal head, again, it's weirdly mapping like more derived than Lucy species or with Ardipithecus. More similar to humans, but it's like barely in the human range, so really what this is kind of telling you is that it's got its sort of own derived feature here. In the relative length of the 4th proximal phalanx, so that weird toe that we were talking about that's like kind of long and strange, it's mapping with Australopithecus afarensis more than anything else. And with regard to the relative depth of the 4th proximal phalanx trochlea, it's mapping more with humans and Australopithecus than it is with the Ardipithecus specimen, the Ardipithecus feet, and the African apes. So what this is telling you is exactly what we already know, right, from looking at the Burtele foot stuff earlier, but quantified really nicely here, that the Burtele foot overall is more primitive than the Australopithecus afarensis or human feet, but that it is more derived than Ardipithecus, which came before it, meaning it is doing its own thing, and it does kind of fit snugly between the primitive to derived morphology that we see in Ardipithecus to Lucy species, or Australopithecus afarensis. That's really cool. And that's where I would suspect, just putting this out there early so you can be sort of chewing on it, that's where I suspect Australopithecus anamensis, the first member of Australopithecus, would fit too. In fact, it would probably be a little bit more primitive than Australopithecus diorama. What this means functionally is summarized here by the last sentence underneath that figure, where they say collectively these lateral forefoot and midfoot traits suggest that the Burtele hominin lacked the structural longitudinal arch and derived push-off morphology of Australopithecus afarensis and may have retained some midfoot mobility useful for climbing. That makes sense because it has that abducted big toe, that big opposable toe for climbing too. At this moment, I'm going to take a minute and show you the Burtele hominin juvenile ischium, just so you can see what I was talking about earlier. Here is from the Lawn Chair Anthropology website, and we have a nice comparison of the Burtele ischium from Australopithecus diaramida, this new ischium, compared with Australopithecus africanus and a more derived hominin, Hominoleti. It looks like a typical Australopithecus ischium is the long story short. But this will probably tell us a lot of cool developmental stuff later in time as we continue to investigate it, because it's one of the only juvenile or like kid ischia that we have. We're going to touch on a few taxonomic ideas, hit the diet, and then start to wrap things up here. They say the inclusion of the Burtele foot and Australopithecus diaramida further demonstrates that the latter species is also more primitive in its foot morphology than Australopithecus afarensis. Okay, cool, we know that. Conversely, some aspects of the first and second metatarsal of these Burtele material are similar to Australopithecus africanus from Sterkfontein than to Australopithecus afarensis. Diaramida and africanus, who's found in South Africa very far away from this site in Ethiopia, have also previously been shown to be similar in maxillary shape than either is to Australopithecus afarensis. A parsimony analysis to assess the phylogenetic position of Diaramida has previously shown that it is sister to a clade containing Africanus, Paranthropus, and Homo, with some dentagnathic homoplazy. The inclusion of the Burtele foot into Australopithecus diaramida's hypodyme and its morphological similarity in some aspects of its morphology to Africanus further highlights the close relationship between these two taxa. My takeaway from that is that it's possible that Australopithecus diaramida and Australopithecus africanus and Australopithecus afarensis all three sort of descend from Australopithecus anamensis, and that afarensis is just the most derived of the three. The reason why diaramida and africanus share some traits is because they just retain them from anamensis, whereas afarensis has sort of moved off in its own direction. The diet stuff is really cool, in part because it's so easily summarized. I love when data is just really easy to depict and it just hits you with the point right off the bat. And the point here is that on our y-axis we have species, and on our x-axis we have our C13 percentage, and we're just looking, this is an isotopic analysis of tooth enamel to try to suss out what these guys were eating, C3 plants or C4 plants. In an overly simplistic explanation, C3 plants include things like leaves and fruit, and C4 plants include things like grasses and sedges. So what you're seeing here is the diet range for various species, and what you can hopefully see is that we see a C3 dominated diet for Australopithecus diaramida, ramidus, and anamensis. One of these three, which we know for a fact is spending a ton of time in the trees, in the form of Ardipithecus ramidus, which is eating a lot of fruits and things like that. So all three of these guys are doing similar things. That has some serious implications for Australopithecus anamensis, but we'll touch that in a second. Whereas afarensis and Kenyanthropus platyops are eating everything. They're eating everything on the landscape. They're eating leaves and fruit, and they're eating grasses and sedges, and they're probably also exploiting animal resources like invertebrates, small mammals, and maybe even things like bone marrow if their tool use is anything to go off of, because both Australopithecus afarensis and Kenyanthropus platyops, whether you lump them or split them, are associated with stone tool use. They summarize it here at the bottom. Species such as Australopithecus afarensis and Kenyanthropus platyops utilized a wide range of both C3 and C4 resources. The lower values for the Burtele hominin teeth, with more limited distributions and their similarity to those from Ardipithecus ramidus and Australopithecus anamensis, indicate that the Burtele hominins may have retained a dietary strategy of older, more primitive hominins, corroborating morphological observations. And, by the way, keeping them from having to directly compete with one another. Australopithecus afarensis is eating everything, whatever it feels like, whereas Australopithecus diaramida is exploiting those arboreal resources primarily, a trend that is continuing from probably the common ancestor of them both. That's super cool. So now we get down to the discussion and the conclusion, and they're going to talk about a lot of stuff that we've sort of been hinting at, so let's buzz through this. The first paragraph just summarizes the sort of dental characteristics of Dioramida and notes that in most characteristics, it's just dentally primitive compared to Afarensis and resembles the probable common ancestor of them both. The second paragraph discusses the enamel isotope analysis with relation to diet, and it sort of ties that into locomotion. I like this bit here. Previous studies have highlighted the variability in early Australopith foot morphology, indicating diverse bipedal forms, each with variable pelvic, limb, and foot morphology. We know this to be true. I've covered the other two categories of this, the non-foot stuff, the pelvic and limb stuff, on this channel before. Current evidence has suggested that some species, such as Dioramida, Africanus, and Australopithecus sediba, remained capable climbers, whereas others, such as Australopithecus afarensis, were more terrestrial. I don't think I've talked about it specifically, but there's a wonderful little bit by Jeremy De Silva in his book First Steps that talks about how Australopithecus sediba, who is pretty derived and lived in the pretty recent past at like 1.98 million years ago, kind of walked in a weird way. Like, looking at its leg and foot morphology and ankle morphology that we have, it walked in a way that was pretty different from what we see in Australopithecus afarensis, and probably is maintained from an earlier, more primitive form of bipedalism. It was definitely bipedal when it was on the ground, but it did so in a different way and still hung out a lot in the trees. The mosaic craniodental and postcranial morphology of Australopithecus Dioramida raises questions about skeletal integration and confirms that post-canine megadontia, that's getting the teeth behind the canine, so the premolars and the molars, it's them getting really big, and obligate human-like bipedality did not evolve simultaneously. I would say that this probably adds additional evidence to that, because that's kind of been a long time coming. The origin of Australopithecus correlates with increased craniodental size, possibly linked to the selection for smaller canines and premolar molarization, preceding full obligate bipedality. The final paragraph summarizes things. Although mid-Pliocene hominin paleobiology and locomotion remain incompletely understood, the Burtele foot confirms the presence of multiple bipedal forms during the Pliocene. Further postcranial fossil discoveries, particularly of early species such as Australopithecus anamensis, will be crucial to fully understanding the origins of obligate human-like bipedality. Okay, let's highlight some key takeaways here if we are to accept this paper, and I do. I think it's a well-argued paper, and I suspect that everyone else is going to accept it too. Number one, Australopithecus Dioramida is legit, and it's the owner of the Burtele foot. That foot morphology, in addition to the isotopic analysis of the tooth enamel, explain how Australopithecus Dioramida is able to, or was able to, exist on the same landscape as Australopithecus anamensis without them having to compete with one another. Dioramida was exploiting primarily arboreal resources, which it got to using, in part, its big opposable toe. One, that means that hominin contemporaneity has just been pushed even further into the past, further underscoring the growing notion that hominin sympatry, or more than one hominin living on the landscape exploiting different resources, is the rule rather than the exception. But also, the fact that Dioramida is giving us the same signal as the earlier hominin, Australopithecus afarensis, the first Australopith, seems to suggest that Australopithecus Dioramida's morphology is probably more similar to anamensis than afarensis's morphology is. And what that would mean is that Australopithecus anamensis may have had the same foot as Dioramida did. And that would mean that all of genus Australopithecus isn't characterized by that inline big toe and the three arches in the foot. That's derived for the latter half of the genus's existence. And in fact, the earliest Australopiths weren't too different from the Ardipiths that came before them. Also, there are those weird similarities between Dioramida and Africanus, and it leaves me wondering how these hominins are all related to one another and to anamensis. How is Barrel Ghazali and Dioramida and Afarensis and Africanus and anamensis, how do they all fit with one another? Who begets who and when? Who's the outgroup? I don't even know how we're going to begin to disentangle that, but I think it's worth noting here that while I was researching for this video, I read a paper by Jeremy De Silva. In it, he goes over the sort of foot evolution and major relevant fossils for our known hominins. Of course, he talks about Afarensis and the Burtele foot, now Dioramida, but he also mentions a specific collection of fossils from Sterkfontein that are all assigned to Australopithecus africanus, a single species. And he's toying around with the idea that maybe we're not looking at a single species in that assemblage. Maybe we're looking at more than one. And his reasoning is that two first metatarsals, that really critical bone for determining whether or not the hallux is divergent, that is to say abducted, or like in line with the rest of the toes, adducted. There's two first metatarsals assigned to Australopithecus africanus that come from member 4 of Sterkfontein, and one of them appears to be in line, and the other appears to be divergent. I've talked about this before on this channel, but there's this phenomenon that happens over and over again in paleoanthropology, where new hominins will appear in Eastern Africa, and then shortly after that, they'll appear in South Africa. And the general idea is that they evolve in Eastern Africa, and then a green highway allows them to sort of migrate downwards and establish a population in South Africa. But that green highway isn't always there. It comes and goes. And so these populations end up kind of stranded in South Africa, where they evolve in really interesting ways. For a really long time, it's been thought that Australopithecus africanus descends from Australopithecus afarensis, who descended from Australopithecus anamensis in Eastern Africa and then traveled via that green highway south to establish a population in South Africa. If these two first metatarsals at Sterkfontein have been correctly characterized, we have a really big mystery on our hands, because the most recent dates for those metatarsals, and indeed for all of member 4 at Sterkfontein, have it at about 3.4 million years of age, the same age as the Burtele foot. The oldest Australopithecus afarensis material is at about 3.9 million years of age, but I think the idea that afarensis is the parent of Diorama and whatever the hell is going on in Sterkfontein member 4, I don't think that holds a lot of water at present. So if afarensis isn't the parent species of Africanus and whatever else is going on in Sterkfontein member 4, who is? The obvious go-to answer here is that Australopithecus anamensis is what ends up begetting everything. It begets Ghazali and afarensis and Diorama and Africanus and whatever else is lurking there in Sterkfontein member 4, and maybe even Kenyanthropus platyops. But we can't know that until we find an Australopithecus anamensis partial skeleton to actually figure out whether it has the appropriate basal morphology across its skeleton to be the parent for all of these. Because the alternative is that it might be a member of Ardipithecus that is the parent species of at least some of these Pliocene hominins. And if that's the case, a lot of things are a lot more paraphyletic than we've been previously giving them credit for, and hominin diversity is even richer than we've previously appreciated, which seems to keep happening. How exciting! Obviously, there are still a lot of open questions, but luckily, open questions are like the engine of human curiosity, so I welcome them. If you like what I do here on this channel and you want to support me in the free way, you can do that by liking, commenting, and subscribing. It helps YouTube recommend my channel to other people who might find it interesting. If you want to support me in a more financial way, you can join my Patreon. Patrons sometimes get early access to videos when I'm on top of things, which is always variable, but they do always get their names at the end of every video, or virtually every video. From the bottom of my gentle and of course very modern heart, I'd like to thank you for being such a curious primate, and I'll see you real soon in the next one when we have that 100% complete Australopithecus anamensis skeleton and we can finally answer all our questions.